Right, hello team. Notes for Tuesday, 10th of May, and today we're going to be talking about the laws of thermodynamics. As you know, I'm not here for the rest of this week. I apologise, out of my control, unfortunately. But yesterday we did talk about the gas laws, and that's going to come into play today. Gas laws being how if you raise the temperature of a gas, the pressure increases or the volume increases, and that's going to come into play today. So, we also talked yesterday how the gas laws affect certain technologies, my favourite being air conditioning. How you compress a gas, it gets hot, that loses its heat outside, comes in, it decompresses, gets cold, that cools down the house. Well, another technology that uses those gas laws is your Mark 1 car engine. Now, I don't know how much you know about car engines, but I'm going to talk about it quickly because it is kind of useful for what we're talking about. Your average car engine is what we call a four-stroke engine, meaning there's four strokes where the piston goes down as the first stroke goes up, the second stroke goes down, the third stroke goes up, the fourth stroke. And each stroke has a different job. As it first goes down, it sucks in air and gasoline, or maybe the gas is squirted in later. And then the intake valve here that lets the air and gasoline in, that shuts as it goes back up, and all of that air gets compressed. And then you have your spark plug. If you have a spark plug, this shows a fuel injector, but you have a spark plug, just lets off a little spark, and the gasoline in this compressed air goes bang, it explodes, gets very, very hot, and because that gas gets very, very hot, in your Mark 1 explosion, the gas gets hot, it creates a huge amount of pressure that pushes down the piston, which in turn turns the crank, what we call the crankshaft, the bit that actually rotates and is connected to your car wheels. And then finally, as the piston goes back up, all of that air that is now exhaust air, because it's been burnt, that goes out the exhaust valve. This four strokes are called the intake stroke, the compression, the power, exhaust. I'll be honest with you, I always learnt it by suck, squeeze, bang, blow. I know that sounds funny, but you suck in the air, you squeeze it, it goes bang, and then you blow the air out on the way out. And right here is I've got myself a lovely Giphy GIF to show this. But it is a good example of the first law of thermodynamics because it shows how heat can do work. Right? How do you get heat? How do you get temperature to do work? So think about the energy flows in a car engine. First of all, you have chemical energy. The gasoline has a lot of chemical energy locked into those chemical bonds. When that has that activation energy, which is set off by the tiny little spark, that ignites, and that chemical energy turns to heat. That heat then does work, right? Just as we were talking about, the heat raises the temperature of the gases inside the piston. That increases the pressure inside the piston that pushes that piston down. Remember, the very definition of work is applying a force over a distance. So as these gases expand, they apply a force over a distance on the piston. It does work. And then that work is then stored as kinetic energy, actually rotational kinetic energy, as it twists around. I think this Giphy GIF really shows very well how that all works. But again, we've got a flow of energy from chemical energy to heat to work to kinetic energy. So, that being said, what has this got to do with the first law of thermodynamics? Well, the first law of thermodynamics basically says how work and temperature is related. And it's very simple. Just as a reminder, temperature, you know this already. Temperature is the average kinetic energy of molecules in the system. Remember, some molecules have more energy, some molecules have less energy, but is the average kinetic energy of the molecules in the system. Well, there's a new thing we need to know about, which is internal energy. That is the total kinetic energy of all the molecules in the system. If can I pause it? Hang on, I can't pause it. The total kinetic energy of all the molecules in the system. If you think of when that gas in the chamber explodes, all of that energy is internal energy. All of that heat energy is called internal energy. Now, it is also called waste heat because any of that chemical energy in the gasoline that gets turned to heat, any of that heat that comes out of that exhaust pipe is wasted because it did not get turned into work. And this is where the first law of thermodynamics comes in. Basically, it says whenever you add heat to a system, it's going to either increase the temperature of the system increase the internal energy of the system, or it's going to do work. And it comes out with this equation. When you add heat to a system, for example, when that gasoline explodes, the amount of heat you add to that system is going to equal, and heat is in joules, remember, heat is in joules, that's going to equal a certain amount of work that you do in joules plus an increase in internal energy. And the symbology for that we use is Q is heat, W is work, delta U is internal energy. That is the first law of thermodynamics. So again, the amount of gasoline you put in, that can get turned into a certain amount of heat. That heat can either do work. Obviously, the more gasoline, it means the hotter the explosion, means the more work, the more force it's going to push down that piston. But there's always going to be some waste heat coming out of it. That's what we call internal energy. It's heating up the engine. It's leaving the system in the exhaust pipe. Obviously, engineers are going to want to do more work, right? For the amount of heat you're putting in, they're going to want to have more work done out of that heat and have less waste heat. So a lot of the engineering in car motors, ship motors, plane motors goes into reducing that waste heat. And just so you know, for a gasoline engine, if you look at the latent energy inside gasoline, the amount of actual work that gasoline does is only about 40% of the heat in that gasoline. 60%, and that's a very efficient fuel engine. It's about 30, 35, 40 is about the most efficient diesel engine. 60% of that energy in the gasoline is wasted as heat, in friction, in noise, all these other things. Only about 40% of the energy in those chemical bonds in the gasoline, in the diesel, goes into actually doing work, turning the engine, moving the car. That, in a nutshell, is, well, this equation is the first law of thermodynamics. Alright, so that's the first law of thermodynamics. Basically says that you put heat into a system, that heat's going to get turned into work, and whatever of that heat is not turned into work just leaves as waste heat. Second law is the tricky one. Second law is a bit of a mind bender, and I'm just going to ask that you do your best with this. But it is a fascinating idea. It involves this thing called entropy. What is entropy? Entropy is a measure of disorder. The lower entropy, the more ordered a system is. The higher entropy, the more disordered a system is. What on earth do I mean by that? Well, I'm glad you asked. So let's look at this real simple graphic. So if you imagine a box with a little partition in it, and you've got a load of blue marbles and you've got a load of red marbles. All the blue marbles are on the left, all the red marbles are on the right. I think we can all agree, you can look at that, and that is a really ordered system. Everything's in its place, everything's nicely ordered. If you go ahead and remove that partition, you shake it, shake it, shake it, all of a sudden you're going to get all these marbles are going to settle back down again, but it is really disordered. They are all mixed in, messed up all over the place. This is a high entropy system. When they're nicely organized, it's a low entropy system. But when they're all mixed up, it is a high entropy system. Where do we go from there? Well, the second law of thermodynamics basically states that entropy in a system will always increase. When you have a system and you do anything to that system, you are always going to go from an ordered system to a disordered system. Now, this honestly makes perfect sense because there's two things. I don't want to get too much into this, called microstates and macrostates. Look at this little marble right here, this guy here. This position, it can be one of two microstates. It can either be blue or it can be red, right? Now, what you have is you have a whole bunch of marbles. I forget how many there are, but let's say 100 different marbles. And each of those can have two microstates. It can either be blue or red. The macrostate is looking at all of this. This is one macrostate, right? Where all the blue balls are on the left, all the red balls are on the right. Here's the thing, there's only two microstates, but I did the math on this a while back, and there are a ridiculously high amount of macrostates, right? If I shake this box up, this is one of the potential macrostates. It is very disordered. But the thing is, if I was to shake it up again, then I will get another thing that will look completely different to that, but will be equally disordered, right? It's almost like if you think of a deck of cards, and they're all in that ace, 2, 3, 4, 5, 6, order for the hearts, then the clubs, then the spades. That is a very low entropy system. you shuffle it, shuffle it, shuffle it, then you're going to go to a high entropy system where they are all in a crazy random order. Now, there are billions, probably, I'm guessing probably even billions of different combinations of random orders. Many different macro states. There's only one micro state in which they are ordered. So basically what the second law of thermodynamics says is you are always going to go from an ordered system, and if you shuffle the deck, you shake the box, you're going to go from an ordered system to a disordered system. Okay, what does this mean for thermodynamics and heat? Well, what this means is if I have a cup of coffee that is hot and I put it in a room that is room temperature, the heat from my cup of coffee is going to mix evenly with the the lower heat molecules in the room, and it is going to even itself out. It means that heat will always flow from hot to cold. You are never going to get my cup of coffee, my hot cup of coffee in the room. I'm going to leave it on my desk. It's not randomly going to get hotter, because that means I'm somehow making the system more organized by putting all of that energy into the one place. You know what I mean? Taking all that energy and like pumping it into my cup of coffee. No. I have a high energy cup of coffee. That energy is always going to disperse randomly around the room. And we're going to get to a point where the internal energy of my coffee, internal energy of the room are equal to each other. So basically my coffee is not going to absorb heat from the air and become hotter. It is always going to become cooler. Now I say that, there's always a slight chance that I could get this box here, shake it, and I could get this macro state here, right? There's always a chance that you could shuffle a random deck of cards and it could become 1, 2, 3, 4, 5, ace 1, ace 2, 3, 4, 5, 6. It could become more ordered. It could happen. But in this situation here, there's a 1 in 5.4 times 10 to the 39 chance that will happen. It ain't going to happen. It's never going to happen. It could happen, but it's never going to realistically happen, right? That is the second law of thermodynamics. The second law of thermodynamics always says that systems go from organized to disorganized, that heat will always go from an area of high concentration to a universal low concentration. There's more I can say about this, but I'm not going to do it because it's a video and I'm running out of time. The final thing I do want to say is, look, my desk. I cleaned it like 2 years ago, and I had to take a picture of it because I rarely clean it, and I was very impressed with myself. And that is a relatively low entropy system. Normally, my desk is a very high entropy system. So I guess the question is, how did I go from a high entropy system, very disorganized, disordered, chaotic, to a organized, orderly, low entropy system? The reality is I had to do work. I had to do work to do that, you know. To fight the entropy, I literally have to do work and energy in organizing it. By putting, by making my cup of coffee, I have to do work with the kettle and everything by getting all of that energy and pumping it into the one place, organizing it into that, all that heat energy into my 1 cup of coffee. So you can fight entropy, you just got to use energy to do it. So anyway, that'll do. I'm just going to turn you over now to the exit slip, which I do want you to answer on the Google Classroom. Alright, exit slip I would like you to do on the Google Classroom. And it's this question: a new ship has a choice of 2 types of engines, propulsion. They both use the same amount of fuel per hour. First one has an exhaust temperature, diesel engine has an exhaust temperature of 650 degrees Celsius. A turbine engine has an exhaust temperature of 425 degrees Celsius. So based purely on how hot the air is that comes out of the funnel of the ship, which one of these 2 engines is more efficient? If you understand the first law, second law, mainly the first law, you should be able to figure that one out. Which of these 2 engines is more efficient? Do you get more efficiency, more work out of the fuel? That's it. I'm going to sign out. Put your answers on the Google Classroom, and I will see you next. Well, I'll make a video for you tomorrow. All right, that'll do. Wired out.